You're probably familiar with a device known as an Atwood's machine. The classic case of an Atwood's machine are two different masses suspended over a pulley. Maybe the larger mass on the right is M1 and the smaller mass on the left is M2, such that this whole system accelerates in this direction. I'll spare you the derivation for now, but you probably recognize that the acceleration of this system would be equal to free fall acceleration multiplied by a ratio that has to do entirely with the amount of mass. I believe we would say that this is M1 minus M2 divided by the sum of M1 plus M2. Except wait a minute, there's some caution to this. We've made some large assumptions here. That equation's only correct assuming the pulley has no rotational kinetic energy. So either the pulley is massless, which I don't know where you buy a massless pulley, or maybe it's rusted so that it's frozen in place, and the string, instead of making the pulley rotate, the string is made of silk or something like this, and it just slides over the top of the pulley that's frozen in place. But what about real life? How does this stuff really work? Well, if the pulley does rotate, then the acceleration is going to be something less than g times m1 minus m2 over the quantity m1 plus m2. How much less? Well, it depends on whether our pulley is a solid cylinder or a hoop. You say, how could it be a hoop? How do I make contact at the axle? Well, maybe there's an axle and then some lightweight spokes. Okay, so the overall mass of our cylinder or hoop would somehow factor in. So as an example, let me do a different modified version of an Atwood's machine. Instead of both masses hanging vertically, you've probably studied cases before where the pulley sits on the edge of a desk and one object slides across a very smooth surface. We'll say the coefficient of kinetic friction is practically zero. So M2 is on a horizontal frictionless surface and M1 hangs vertically. And how about we say it happens to be a solid cylinder of mass capital M. So there's two approaches to figuring out what the acceleration of the system is. Approach number one, you've probably already done this before. From conservation of energy principles, we can figure out the acceleration of the system. So let's give that a shot. If we animate this, then eventually mass number one will have fallen through a height of h. It will have gained a translational velocity of v, which would be the same as the distance that mass number 2 has traveled, and because they're attached by one piece of string, they share common motion, so mass number 2 gains some velocity, but at the same time the cylinder begins to rotate and gain some angular velocity. So it's all the loss of gravitational potential energy of mass number 1 that results in its increase in kinetic energy, the increase in translational kinetic energy of block 2, as well as the increase in rotational kinetic energy of the pulley. So gravitational potential energy of block number 1 equates to the translational kinetic energy of block 1 plus the translational kinetic energy of block 2 plus the rotational kinetic energy of the pulley. So mgh is equal to m1 times gh is equal to 1/2 m1 v squared plus 1/2 m2 v squared plus 1/2 I omega squared. Okay, so in place of I, rotational inertia, a solid cylinder has a rotational inertia equal to 1/2 of its mass. Here we're using capital M as the mass of the pulley, and then we'll use capital R as the radius of the pulley. And the formula for rotational inertia is 1/2 mass times radius squared. And then we'll say a point on the rim of the pulley where the string attaches has a tangential velocity that's equal to the angular speed times the radius of the pulley. So if we flip that equation around, we can say that the angular speed is the tangential velocity divided by the radius, and then that gets squared. So the r that gets squared cancels with this r squared, and then we're left with v squared here. So we can factor out the v squared. We can say m1 times gh is equal to 1/2 m1 plus 1/2 m2 plus 1/4 capital M, all multiplied by v squared. And from kinematics, if this block started with an initial speed of 0 and travels a distance h, then there's a kinematics equation that says its final speed squared is its initial speed squared plus 2 times its acceleration times its displacement, and the initial speed was 0, so v squared can be substituted with 2ah. If I multiply through by 2, I get 2 m1 gh is equal to m1 plus m2 plus 1/2 capital M, all multiplied by v squared, which is 2ah. So then I can cancel out these 2's, and I can cancel out the h. So I'm left solving for a, and a is equal to g times the quantity m1 divided by m1 plus m2 plus 1/2 the mass of the pulley. Now notice, if this was the idealized case, where the mass of the pulley was practically 0, then the acceleration of the system would be g times m1 divided by m1 plus m2, which would indeed be the case for the massless pulley. Okay, so can we derive this equation and get the exact same result a second way? Conservation of energy applies to this problem without a doubt, but so should the new equations that we're learning in this unit, one of which says the sum of all external torque is equal to rotational inertia times angular acceleration, and torque is defined as a cross product of lever arm with force. So how can I use these equations to derive the exact same result? Let's give it a shot. Without taking into account conservation of energy, just considering force, we have 3 force diagrams. One force diagram is for block number 1. So if the whole system is going to accelerate in this direction, then I know whatever is pulling down on block number 1, I guess that's the weight of block number 1. That's a vector that's going to be greater than the upward pull. Now the upward pull is provided by the tension in this segment of string. I'll call that T, but I'm going to give a subscript there. I'm going to call it T number 1. The only way this pulley could rotate in a clockwise direction is if the string grips the pulley as opposed to slides freely over it. Then in that way, wherever the string is gripping here, it provides a downward force onto the pulley this way, and the tension in this part of the string actually pulls back this way. So if I draw forces on the pulley, there's a downward force from this segment of the string, and there's a force to the left from this segment of the string. It's like a tug of war, right? If we zoom in a little bit, the string grips the pulley at that point, and the string also grips the pulley at that point, and there's a downward pull this way, and there's a pull to the left this way. So as long as T1, the tension in the vertical segment of the string, is greater than T number 2, the tension in the horizontal segment of the string, then you could indeed have some clockwise rotation or develop some value of angular speed, omega, for the pulley. Let's draw the free body diagram for block number 2. It has some weight, but there's a normal force to cancel it out. So all that really matters is, and we're saying that it's frictionless. So the only pull on block number 2 that provides any acceleration, if the tension is pulling in this segment of string to the left on the pulley, then that same string is pulling to the right on our block number 2. So let's write some equation based on Newton's laws. It looks like the net amount of external force, even though there are 1, 2, 3 forces, only one of them remains, the net force on block number 2 is just equal to tension number 2. So mass of block 2 times the acceleration of the system is equal to tension 2. We're going to use this equation here in a moment. Here, the sum of all forces on block number 1, M1G, minus tension number 1, or M1A equals M1G minus T1. We're going to use that equation. Now there's a problem. We have 3 unknown quantities. We don't know the acceleration of the system, we don't know the tension in the horizontal segment of the string, and we don't know the tension in the vertical part of the string. 1, 2, 3 questions. We've already stated that we don't know A. So for 3 unknowns, we need 3 equations. The third equation comes from making a diagram, and I'm not going to call it a free body diagram in this case. I'll call it a rigid body diagram. Because here I'm not going to just replace the pulley with a dot like we typically do. Notice I substituted block number 1 with a dot. I'm actually going to draw the forces as they are applied on the pulley. So let me draw a larger version of the pulley, locate the center or the axis of rotation, and then indicate all the forces that are acting on the pulley. Actually, I'm not going to indicate all of the forces. Some of the forces are aligned with the center of mass of the pulley. And when a force passes through the center of mass, it provides no torque. This would be sort of like coming up to a door whose knob is right here and hinges are over on the left. And generally, when we try to open a door, if you're anything like me, you like to push on the doorknob. And so you have a push that points, well, in this 3-dimensional drawing, your force points into the page, and there's a lever arm that points from the axis of rotation in the hinges out to the place where that force is applied. So in 3 dimensions, the angle between the lever arm and the force is 90 degrees, and then you get a rotation, and you can use the right-hand rule. If you curl your fingers in the direction the door is going to rotate, you see your thumb points upward, and there's the direction of the torque. But if somebody else were to come up to this door, and aren't there often doors like this, instead of having a knob, sometimes you approach a door and it has, what do they call it, a panic bar? And so you don't know, am I supposed to push on this side of the door to open it or this side? Because sometimes it's not clear where the hinges are located. So let's say all the hinges are on the left, and you try to exit through this door, and without knowing it, you walk up to it and unwittingly push on this side, and the door doesn't open at all. It's not because your force is 0, right? You're applying a significant amount of force, but there's practically 0 lever arm, and so the torque is very nearly 0. So it's not just how hard you can push, it's providing your push with the greatest possible lever arm that gives you a lot of torque. And that's what people are talking about when they say you need to try to get more leverage out of your effort. So back to this problem. The weight vector for this pulley is a vector that we can say acts at the center of mass. So even though the pulley has a weight, there's no torque associated with that force because it acts right at the axis of rotation, and so there's no lever arm to go along with that force, so it's a non-torque producing force. We only want to show the torque producing forces on our rigid body diagram. Likewise, there's some sort of strut that holds the pulley in place and attaches it to the desk. But that strut attaches to the pulley at the center of mass, at the axis of rotation. And so maybe we'd describe this as being a normal force. But it has no lever arm. So you know what? I'm going to draw this diagram again and say I'm going to disregard the normal force from the strut and the weight of the pulley because those are non-torque producing, and I'm only going to show the torque producing forces. And what are they? Well, one of them is the tension. Now notice there's a lever arm that goes along with that force. The tension is applied at that big of a distance from the axis of rotation. In fact, that's nothing more than the radius of the pulley. Then there's a second torque-producing force. It's the tension in the horizontal piece of string, pulling back this way. Now it also has a distance from the axis of rotation that happens to be the radius of the pulley. And how about this? In this case, the angle between the lever arm and the force is 90 degrees for both forces. So let's label these forces once again. This is T1, the tension in the vertical string. This is T2, the tension in the horizontal string. And instead of saying net force equals mass times acceleration, here we're more interested in torque than force. We'll say the net torque is equal to the torque that's going to make it rotate in a clockwise direction minus the torque that makes it want to go back the other way in the counterclockwise direction. And I think you'd agree with me that this tension acting at a lever arm shown based on the right-hand rule would be the one that produces clockwise rotation. And when you apply a force to the left with a lever arm that points up, you get a counterclockwise rotation. So the net amount of torque is going to be the torque in the clockwise direction minus the torque in the counterclockwise direction. Or in other words, the net torque that acts on our pulley is equal to, how do we calculate torque? Torque is the product of, at least in magnitude, force times lever arm times sine of an angle. But in this case, we identified the angles are 90 degrees, and the sine of 90 is equal to 1. So the clockwise torque is just tension number 1 multiplied by a lever arm of capital R multiplied by the sine of 90 degrees. So it's T1 times R. The torque in the counterclockwise direction is T2 times R times the sine of 90 degrees. So it's T2 times R. So here's where we invoke the rotational analog to Newton's second law. Just like net force can be substituted with ma, net torque can always be substituted with, right, I alpha. So we get to say I alpha is equal to T1R minus T2R. Now what's I? What's the rotational inertia for a solid disk? Isn't that what we said the shape of our pulley is? It's the solid disk, not the hoop. Right, the rotational inertia of a solid disk is 1/2 mr squared. So 1/2 mr squared times alpha is T1 minus T2 quantity times r, if you allow me to factor out. So I can cancel that r with one of these r's, and now I have a substitution I can make in place of alpha, just like the displacement along the perimeter of a wheel is called S when the angle is theta, and S equals theta times r. If I take the derivative of both sides of that equation, then I get ds dt equals r d theta dt, but that's just the same thing as saying v equals omega r. If I take the derivative once again, d dt of v equals d dt of omega r, then I get dv dt equals r times d omega dt, and that means linear acceleration is r times angular acceleration. Or better yet, angular acceleration is linear acceleration divided by radius. Whew. So I'm going to make that substitution. So I'm finally left with 1/2 capital M times r multiplied by a over r is equal to T1 minus T2. And now the r's have completely canceled out. So let's summarize all of the equations we have. 1/2 times capital M times A is equal to T1 minus T2. And that goes along with this equation. T2 is equal to M2A, or M2A equals T2, maybe is a better way to say it. Right? M2A equals T2, M2A equals T2, and then M1A equals M1G minus T, M1A equals M1G minus T. Which T is that? That's minus T1. Stick with me, I know we're going through this the long way. Now that I have 1, 2, 3 equations for 1, 2, 3 unknowns, it should all work out. And in fact, it simplifies quite nicely if I just add all the equations together. There's an A in that term, there's an A in this term, and there's an A in this term. So when I add them all up, I could just factor out that A. So I'm going to have A times 1/2 capital M plus M2 plus M1. And then look at this. I've got a positive T1 and a negative T1. So those cancel out. I've got a negative T2 and a positive T2. So those cancel out. So I just got rid of 2 unknowns. The vertical and horizontal tension cancel out when I add this up, and then all I'm left with is just the M1G on the right side of the equation. So if I just divide and rearrange a little bit, I get A is equal to G. We got our A and our G, and then times M1, and then divided by all of this, which I'll write in the other order. I'll write M1 plus M2 plus 1/2 M. M1 plus M2 plus 1/2 M. Does that look familiar? Let's see. Scroll back up. Sure. That's the exact same result we got when we applied the law of conservation of energy to solve this problem. Now, you might say, that was a much quicker and easier approach. Well, it did take fewer steps and it didn't require any free body diagrams, but it also might seem easier for now because you're probably just coming from a chapter in which you were studying in depth the way in which energy relates to rotation. So in this unit of study, There's just a change in our approach, a change in the way that we look at the problem, and we're going to think of rotation in terms of torques. If we were to go through this derivation one more time, I don't think I would take as much time to explain every step of the work, and we could get this same result in a much shorter amount of time. In fact, I'd leave it up to you to, after you watch this video, get a couple of pieces of paper of your own and draw this modified version of the Atwood's machine, and this time replace the solid disc with a ring or a hollow cylinder or a hoop or whatever language you prefer, and see if you can figure out, oh, I'm not sure I like the way I drew that, do-overs. Right, draw the modified version of the Atwood's machine. There's your mass number 2. Your pulley this time is in the shape of a hoop instead of a solid cylinder. A string passes over the rim of it. There's a strut that attaches to the center of the hoop, and so maybe there's a few little lightweight spokes, and then we've got mass number 1. Well, see if you can make a few force diagrams. Make a free body diagram for block number 2. Make a free body diagram for block number 1, and then make a rigid body diagram for the hoop. And from all of those diagrams, see if you can use these two equations. The sum of all force on any object is mass times acceleration, and the sum of all torque on any object is rotational inertia times angular acceleration. I believe from all of that, you'll be able to derive a result that's similar to this, but not exactly the same, because after all, a hoop is similar to a solid disc, but not exactly the same.